Welcome back to the deep dive, where we take the infrastructure you rely on, peel back the layers, and really expose the sophisticated engineering that's working underneath it all.
hmm
Today, we are diving deep into a topic that, it rarely sees the light of day, but is absolutely essential for grid stability and safety.
It's one of those invisible heroes, really.
Exactly. We're talking about electrical fault protection.
Okay, yeah.
Specifically, we're looking at the unsung heroes of distribution systems, current limiting fuses.
And really how high-tech design ensures that you get immediate, flawless protection, often in pretty hostile environments.
I mean, we're talking underground vaults, submerged, transformer tanks. These are not friendly places for sensitive equipment.
Not at all. And it's such a critical area of study for anyone who's managing utility assets because the difference between, a minor incident and a truly catastrophic failure, it often comes down to microseconds. So our focus today is really on understanding this advanced current limiting fuse technology,
Yeah.
the CLF, how it achieves this incredible speed, and the specific application ecosystems that demand this high level of integrity.
That's right. So our mission today for you listening is to unpack the source material we have here and really understand three core application areas for these advanced CLFs.
Yeah.
First, how they completely revolutionize reliability in molded underground systems. Second, their essential role as backup protection for really high-value transformers.
That's a critical one.
And third, the specialized design requirements for what are called full-range fuses that have to operate in completely different thermal environments.
Yeah, and to really get it, we have to start with the fundamental problem that these devices are designed to solve. It's all about managing electrical fault energy.
Okay.
So when a short circuit occurs, the current,
Mm.
it rises almost instantaneously, just a massive spike.
And it's the energy from that fault that does the real damage, right?
Exactly. The destructive energy released during that fault is quantified by a formula. I squared T. I squared T. So that's the current squared multiplied by the time the fault is allowed to persist.
That's the one. And when you look at that formula, the time element, that's the one we really have the most control over.
And what does that energy, that I squared T, what does it physically do to the system if it's just allowed to run rampant?
It creates enormous stress. I mean, both mechanical and thermal stress on everything in that fault path.
So things like switchgear, cables.
switchgear, cables, transformers. Absolutely. Unchecked I squared T can literally vaporize copper conductors. It can cause insulation to fail and can generate these explosive pressure waves inside sealed equipment.
Wow.
A literal physical attack on the infrastructure.
So the goal isn't just to interrupt the current. It's not just about stopping it. The goal is to limit the current and, more importantly, crush that damaging time component. That's it exactly.
Yeah.
And this is where the high-tech current limiting fuses deliver their primary promise. They offer, and I'm quoting some of the material, superior protection in small, cost-efficient form factors.
Okay.
So they don't just interrupt the fault current. They interrupt it so fast that they actually restrict the fault current from ever reaching its potential maximum peak.
Which brings us to this incredible speed capability that's mentioned in the materials. The best of these CLFs. They boast fault-clearing capabilities of less than 1/2 cycle.
Mm-hmm.
For our listeners who are used to thinking in milliseconds, what does that timing actually represent in terms of a standard AC sine wave?
Okay, so in a typical 60 hertz system, right, one full cycle takes about 16.7 milliseconds.
Right.
Half a cycle is roughly 8.3 milliseconds.
Mm.
So when the fuse clears the fault in less than half a cycle, let's say 5 or 6 milliseconds, it means the current is interrupted and completely suppressed before that AC waveform even has a chance to reach its natural peak.
Which occurs at the quarter cycle mark?
Exactly.
That is the technological miracle right there. By achieving that pre-peak limitation, they just dramatically reduce the I squared 2 energy.
It is the absolute game changer. If you prevent the current from reaching its maximum potential peak, you reduce the mechanical forces associated with that fault by orders of magnitude.
That's incredible.
And this speed is what allows utilities to use existing high-value equipment that might otherwise be, underrated for the full fault capacity of a modern substation. The fuse just limits the energy to a manageable level.
So it minimizes stress, it enhances long-term reliability.
And it provides measurable safety improvements, big time.
So the ultimate payoff then is it's about longevity and cost management. By protecting those really expensive assets downstream, these relatively inexpensive fuses maximize reliability while measurably reducing the system's life cycle costs. That's a very strong value proposition.
It is. It really is. So as we move through this discussion, just keep that I-squared-3 reduction in your mind. We're going to see how this core capability shows up in three key areas. The molded elastomold underground systems, the essential backup protection schemes with the OS Shorty and EXT fuses, and then finally, those specialized full-range fuses, the FX and SX series.
Let's do it. Let's start putting the science under the microscope and look at the anatomy required to achieve this stunning performance.
All right. And here's where it gets really, really interesting. To offer this superior lightning-fast protection, these fuses have to be engineered for what's called full-range protection.
And when we say full range, we're talking about a massive gap in current magnitude that they have to reliably handle, right? A huge spectrum.
A huge spectrum, exactly. Full range means the fuse has to be able to interrupt any continuous current between two extremes.
Okay, what's the low end?
The low end is the minimum current that causes the elements to melt. This could be a very low-level, prolonged overload, something that might take hours or even days to materialize.
And the high end?
The high end is the rated maximum interrupting current, which for these advanced CLFs is often a monumental $50,000 symmetrical capability.
50,000 amps. That is a catastrophic short circuit. And they have to reliably manage that alongside a minor overload that's barely even heating the element. How is that capability possibly built into a component that's, only slightly larger than a thermos flask?
Well, it requires a complex, multifunctional internal anatomy. You just can't use one element to do both of those jobs efficiently. So inside the ceramic or epoxy glass body, there are actually two distinct interruption elements working in parallel. You have a very fine, specific, low-current interruption element.
And that's designed with a precise thermal characteristic to handle those long, low-magnitude faults.
Correct. It's designed to melt slowly under that sustained heat, so it acts like a more traditional thermal fuse.
Got it.
But then, right alongside it, you have the separate, robust, high-current interruption element. This one is optimized for those massive instantaneous surge currents, the 50 Ka events we're talking about.
So when that huge current hits, this is the element that ensures an almost instant arc initiation, which triggers the whole current limitation process.
That's the one that kicks everything off in microseconds.
And the mechanism for stopping an arc that's generated by thousands of amps in just a few milliseconds, that has to be extraordinary. What is surrounding these elements to quench that arc so effectively and so rapidly?
That is the role of the arc quenching medium. And in this case, it's finely graded, highly purified, and very, very compacted quartz sand. Quartz sand. When the fuse elements melt and the arc is established, the high pressure and temperature immediately cause those quartz sand particles to melt and fuse together. They form a non-conductive, glass-like substance called a fulgurite.
That sounds like a controlled explosion that builds its own non-conductive barrier instantly.
That's a perfect way to describe it. It's a self-extinguishing mechanism. The sand absorbs the massive thermal energy, rapidly cooling and extinguishing the plasma arc. The quality and the compaction of that quartz sand are absolutely vital to ensure the hermetic seal holds during the immense pressure spike that's generated during interruption.
So the integrity of the physical construction, then, it has to match the speed of the electrical operation. We mentioned several specialized design features earlier. Let's talk about the damage sensor. Why is that an essential feature for a high-integrity fuse?
This sensor, it addresses a really common real-world longevity problem.
Okay.
When a fuse is subjected to a significant but non-interrupting surge, like a nearby lightning strike, for instance.
So a big jolt, but not enough to actually blow the fuse.
Right. Even if the current doesn't melt the main elements, that surge can cause microscopic damage. We're talking stress fractures or localized heating within the elements.
So the fuse might look perfectly fine from the outside, but its internal components have been weakened. It's now compromised, and it might fail catastrophically later on during a future, maybe even a smaller fault event.
Precisely. The damage sensor is engineered to detect this pre-fault degradation caused by transient events. It's a crucial internal feature that significantly reduces the risk of what's called latent fuse failure.
Latent failure, I like that term.
Yeah. It just provides resilience, ensuring that when the next real fault happens, the fuse operates exactly as it was designed to, not with some pre-existing weakness.
That is a very sophisticated layer of internal self-protection. Let's move to the external integrity, which is so vital since these are often used underground or even submerged. The source material really highlights the need for hermetic sealing.
Yes, the construction has to be meticulously sealed to ensure that absolutely no gases escape from the fuse during current interruption. This is a non-negotiable safety feature.
Especially in confined spaces, I imagine, or when the fuse is submerged directly in insulating oil.
Oh, absolutely. Escaping gases could lead to contamination, tank pressurization, or even fire hazards.
But how do they guarantee that level of sealing integrity? I mean, if you're producing thousands of these components, how do you verify that every single one is perfectly sealed, especially if they're going into environments where a tiny leak means immediate failure?
This is where the engineering commitment really stands out. All of these fuses are leak tested using a helium mass spectrometer.
Wow. A helium mass spectrometer. That's the sort of technology you usually associate with checking seals on, like space capsules or high vacuum systems, not utility
You're
consumables.
exactly right.
So why is that level of testing necessary for a fuse?
It's because the mass spectrometer can detect leaks of an incredibly minute size. We're talking parts per trillion. For a fuse that's destined for a submerged environment, even a microscopic pinhole that allows gradual moisture ingress over years that will eventually lead to failure.
Ah, so moisture contamination inside the quartz sand would disrupt the arc quenching effectiveness.
It kills it. So by using helium, which is this tiny inert gas tracer, they can guarantee the sealing system integrity. They ensure the fuse will perform reliably over its entire operational life in the absolute harshest conditions.
That really contextualizes the quality control. I mean, they aren't treating this like a simple consumable, they're treating it like a precision, pressure bearing vessel.
Absolutely. And then finally, mechanically, they use these rugged machine brass end caps. This precision machining provides greater ferrule strength, it secures the fuse attachment, it minimizes any potential distortion from thermal cycling or fault forces, and it ensures an optimal, low-resistance electrical connection to the system.
Okay, let's talk thermal capabilities.
Mhm.
These fuses are going into places where ambient temperature is far from ideal. Hot switchgear rooms, sun-baked pad mount enclosures, or deep in subsurface vaults. How robust are they to heat?
They have to be incredibly robust. They're tested and rated according to something called a rated maximum application temperature, or RMAT.
Arment. Okay.
Depending on the specific fuse type and its application, some ratings specify an RMAT up to 65 degrees C, which is very warm, for air environments.
And for other applications?
Certain specialized designs, like those for oil-filled wet well applications, might even specify RMATs up to 140 degrees C for the insulating oil.
That difference is massive. It really indicates the specialization that's required for the environment. But if the continuous current rating is often established at, say, 25 degrees C, what happens when the actual operational environment exceeds that? Let's say in a subsurface vault that's constantly sitting at 45 degrees C.
That's where the D-rating formula becomes critical knowledge for the specifying engineer. Above that 25 degrees C baseline, the continuous current carrying capacity has to be reduced.
Okay.
The sources give a very clear D-rating formula. The maximum continuous current decreases by 0.2% per degree C over 25 degrees C.
Let's walk through an example. I think that would really help the listener understand the impact of ignoring that D rating. So if we have a vault continuously operating at 50 degrees C, what's the adjustment?
Okay, good example. So 50 degrees C is 25 degrees above our 25 degrees C baseline.
Right.
You multiply 25 by 0.2%, you get a total D rating of 5%. So if you were planning to use a 200 amp fuse, you can now only safely use it for 190 amps of continuous current at that elevated temperature.
So what's the failure mode here? If an engineer failed to calculate that 5% D rating and consistently ran, say, 195 amps through that 200 amp fuse in that 50 degree C vault, what happens?
They risk premature thermal failure. The low current element, which is already designed to melt slowly under sustained heat, will operate prematurely.
A nuisance trip.
A nuisance trip, significant downtime, and unnecessary maintenance, all because the design neglected that crucial thermal coefficient. It's a classic example of why the rigorous application of these D-rating standards is so essential for reliability.
That beautifully contextualizes the engineering behind the device itself.
Okay, so now let's take these high-integrity, high-speed components and see how they're deployed in one of the most challenging environments out there, underground distribution.
Yeah, we're moving from the microscopic view of the element to the massive, complex infrastructure of the molded ecosystem. Right. And for utility managers, the underground distribution challenge often centers around loop systems. If you have a fault, let's say a shovel digs into an unprotected cable tap feeding a few commercial buildings, what is the typical disastrous outcome in a legacy system.
The outcome is system-wide disaster. Because the fault is downstream and it's unprotected at the tap, the entire system relies on the main substation breaker to clear the fault,
So that breaker locks out the entire feeder.
causing a massive outage that affects every single customer downstream on that entire loop until crews can get out there, locate the fault, isolate it, and manually reroute the power. It takes hours.
And the result of that is a dramatically worsened System Average Interruption Frequency Index, SAIFI score,
Yeah.
which is a major utility performance metric tied to regulatory compliance and penalties.
A huge one. So the solution has to isolate the fault locally, and it has to do it quickly. And that's why the introduction of the fused load break elbows, the EFXE, is such a fundamental game changer for underground distribution reliability.
How does the EFXE directly improve that SAIFI metric? Let's use a hypothetical scenario to ground this for the listener.
Okay, let's assume a feeder loop serves 5,000 customers. A fault occurs on a tap that's only serving 200 of those customers.
Right.
In the old system, all 5,000 customers lose power until that fault is isolated. But by replacing the existing standard 200 amp tap elbows with the EFXE, the fault is isolated right at the tap.
So the fault current hits the EFXE, the CLF inside clears the fault in milliseconds, and the other 4,800 customers on the main loop, they never even see the substation breaker trip.
That's the immediate reliability improvement. Only the 200 customers on the faulty tap experience the outage. In terms of your SAIFI calculation, you just went from 5,000 customer interruptions down to 200.
It's the simplest, most effective way to enhance system resilience in underground radial or loop systems.
Absolutely.
And the EFXE is a pretty sophisticated piece of equipment because it combines two critical functions in one fully molded unit.
It's a brilliant integration. It combines the full-range CLF protection with that 50 Ka interrupting capability we talked about, with the functionality of 1,525 kV, 200A, hot stick operable, load break elbow switching.
That hot stick operable part is crucial, isn't it?
It's critical. It means the maintenance crew can safely switch the elbow on or off using a hot stick, avoiding the massive expense and footprint of installing separate switchgear or pad mount cabinets just for fusing and switching.
That integrated design also addresses a pretty fundamental safety limitation of standard load break elbows.
It does, yeah. A standard 200 amp elbow generally has a fault close rating of only 10 Ka.
Okay.
If a crew member closes that elbow into a fault that exceeds 10 Ka, the equipment is likely to fail, and fail destructively.
But because the EFXE has the current limiting fuse inside.
That CLF improves the fault close rating dramatically. It matches the fuse's own high rating, and this greatly reduces the risk of equipment damage, or, more importantly, personnel injury, if they accidentally close the elbow onto a known fault.
Safety and indication are equally crucial when faults happen out of sight underground. What about locating the problem quickly? How do you know which fuse blew?
That's handled by features like the neon voltage indicators, V2. These indicators attach directly to the capacitance test points of the elbow.
Okay, and what do they show?
If the CLF inside the EFXE operates and clears the fault, the load side is de-energized and the neon lights just stop flashing. That immediately signals a blown fuse indication to the personnel without them having to physically open the vault or perform complex testing.
That's clever. And given they are used in vaults, often exposed to water, mud, contaminants, the construction must be totally sealed and submersible.
Oh, it is. They use this rugged EPDM molded rubber dead front construction. This means the units are fully sealed, submersible, and corrosion resistant.
And dead front is the key safety term here, right?
Absolutely. Dead front means that all the conductive or live parts are fully shielded and encapsulated within the grounded EPDM rubber housing. It eliminates exposed live parts and maximizes safety, which is just ideal for radial taps or transformers and faults.
Okay, so moving on from the EFXE, which is that combined elbow and fuse, let's look at the specialized standalone molded current limiting fuses, MCLF. What unique installation flexibility do these modular units offer?
The MCLFs, they emphasize maximum modularity. The fuse section itself is replaceable, and the unit features interchangeable end fittings.
Meaning you can tailor the MCLF for different connection types.
Exactly. Either for standard elbow connections or for direct attachment to high-voltage equipment bushings.
So they provide that same 50 kLA protection, but in a flexible format that can be inserted almost anywhere in the system path.
Precisely. They offer full-range protection. They're suitable for systems ranging from 5 kV up to 35 kV, and typically in a grounded Y configuration.
Which is the most common configuration for distribution systems where the neutral is tied directly to Earth?
That's the one. They're applied across pad mount, subsurface, or vault installations, and always with that explicit goal of limiting the system available fault current to protect those downstream assets.
And rounding out this molded ecosystem, we have the ultimate sealed housing, the molded canister fuses, MCM.
Right, the MCN is the dedicated enclosure. It's a compact, lightweight, maintenance-free package of EPDM molded rubber.
So also dead front and submersible?
Fully dead front and submersible, suitable for systems up to 28 kilo GNDY, that's grounded Y to grounded Y. They essentially act as this highly protective, durable shell for the fuse element itself.
And what fuse type typically lives inside this specialized submersible housing?
The MCN canisters are designed specifically to house and protect the high-tech TransGuard FX fuses, which we'll discuss those in more detail a bit later.
And the sources mentioned models like 22, 66, 62, 66. What do those identifiers mean in terms of mounting flexibility?
They just refer to the end fittings. So model 22 means 200 amp bushing wells on both ends. 66 means 600 amp bushings on both ends. And then the mixed models, like 6E2 and 6E6, they combine elbow connectors with bushing wells or 600 amp bushings, ensuring maximum mounting flexibility to integrate into any existing system infrastructure.
I want to circle back to the operational difference. Unlike the EFXE elbow, which allows for hot stick switching, fuse replacement in the MCN requires the canister to be de-energized first.
That is a critical operational distinction. Because the MCN is purely a sealed enclosure for the fuse, it's not an integrated load brace switch. So personnel must ensure the system is completely de-energized and grounded before they open that canister to replace the FX fuse inside.
It's a trade-off for the superior protection and fully sealed integrity it provides in those harsh environments.
Exactly.
That really sets the stage for how these devices protect underground assets. Now, let's shift focus to one of the most critical safety applications: preventing catastrophic failure in high-value assets, specifically distribution transformers, using a layered, coordinated approach.
Right. And this takes us into the two-fuse protection scheme, the crucial backup strategy. The entire concept here hinges on critical coordination between a primary low-current protective device and the high-current device.
And according to the standard IEEE C37.4G, these must always be used in series. The low current protection device, often an expulsion fuse or a link, is the primary element. What exactly is its job?
The expulsion fuse is responsible for clearing low-magnitude currents. This is vital for standard overloads, high-impedance faults that develop slowly, or external faults that are below the CLF's minimum melt curve.
So it handles the vast majority of common system disturbances.
It does.
But why not just design the CLF to handle those low currents too? If the CLF is so fast and capable, why introduce a second slower component into the mix?
That's a fundamental engineering challenge. A current-limiting fuse is optimized for speed under massive fault conditions. If you try to make a CLF sensitive enough to clear very low sustained overloads, you actually compromise its ability to handle the extreme dynamic forces of a 50 kA fault. Or you make it prone to nuisance tripping.
So they have different complementary functions.
Fundamentally different. The expulsion fuse handles the thermal fatigue and the minor events.
And the current limiting fuse, the backup CLF, is reserved for the true destructive high current events.
Exactly. The CLF role is to clear the massive low-impedance internal faults up to its maximum interrupting capability. And this role is critical because distribution transformers protected solely by expulsion fuses have a major vulnerability.
And that vulnerability relates to their very low interrupting capacity, which is only between 600A and 3500A. So what happens if a catastrophic internal fault exceeds 3500A?
This is the scenario that leads to catastrophic tank failure. If the fault current exceeds the capacity of the expulsion fuse, the fuse element will disintegrate, sure, but the resulting arc continues unabated inside the transformer tank.
And the energy released by that ongoing arc.
It rapidly vaporizes the oil and insulation, generating immense gas pressure.
And that pressure spike is what causes the dreaded transformer tank rupture.
Precisely. The tank rupture is a disruptive equipment failure. We're talking shrapnel, fire, oil, spills, massive safety and environmental risks. And it continues until a distant upstream device, like the substation breaker, finally operates. But that might be hundreds of milliseconds too late for the integrity of the transformer tank itself.
So the goal of the backup CLF is to ensure that even during the absolute worst-case scenario, the fault current is cleared so rapidly that the tank never sees that explosive pressure buildup.
That's the exact function of the TransGuard OS Shorty, which is designed for internal under-oil application. It limits the let-through energy, that I squared T, to a value that is mathematically below the mechanical withstand capability of the transformer tank.
So by limiting the total Arcesian energy, it minimizes those disruptive failures, it saves the asset, and it prevents dangerous tank ruptures.
That's the whole job.
And because it's mounted internally, especially in small single-phase distribution transformers, its physical size must be very compact.
The compact size of the OS Shorty is a major design constraint and a key feature. It allows it to be easily integrated during manufacturing or retrofitted into existing transformer designs without requiring major physical modifications to the tank structure. It's all about putting maximum protection capability into the minimum amount of space.
Okay, now let's shift from under-oil to overhead distribution systems and the TransGuard EXT, the external application counterpart. It's still a backup device, often installed in series with a standard cutout expulsion fuse.
Right, the EXT provides the same superior I squared T limitation, but its engineering includes a really fascinating feature related to system coordination and, well, communication to field crews.
Visual indication.
Visual indication.
So if the CLF operates, it clears the fault internally. That means there's no physical visual cue, like a cutout fuse dropping open. But maintenance crews need to know where the fault happened without checking every single transformer. So how is that visual indication integrated?
It's achieved by careful calibration. The EXT is intentionally selected to allow sufficient let-through current to cause the series cutout expulsion fuse to melt and drop open.
Wait, hold on. You're saying the CLF operates fast enough to protect the transformer, but it allows just enough current to pass through to blow the low current fuse, making the visual indication mechanism drop open.
That is the coordinated genius of the design. The current that passes through is minimal enough to protect the transformer and drastically limit the I squared T, but it's just sufficient to cause the visible action of that primary expulsion fuse.
So it allows field personnel to immediately and visually pinpoint the exact location of the outage. That has to drastically speed up fault location and restoration time.
Immensely.
That is brilliant dual-purpose design. Maximum protection for the hardware, maximum coordination and communication for the personnel.
Exactly. And beyond that, the current limiting action of the EXT offers two other power quality and safety benefits. First, it improves power quality by significantly reducing the voltage dip time during the fault event. And second, it reduces the substantial flame discharge and noise traditionally associated with the operation of the series expulsion fuse, which is a major safety concern in populated areas.
And speaking of capability, the EXT line handles the most extreme fault conditions.
It does. EXT fuses offer the most complete range of ratings, with symmetrical capabilities reaching up to 100 kA at 8.3 kV, 15.5 kV.
100,000 amps.
And they're scalable for sub-transmission applications. For extremely high voltage systems like 115 kV or 138 kV, the application requires assembling and ordering two of the 100K modules, which are installed individually but wired in series to handle that system voltage.
That adaptability shows the core technology is robust enough to span from distribution all the way up to sub-transmission levels just by modular assembly.
The flexibility is key. But orchestrating these two fuse schemes, ensuring the expulsion link clears the low current and the CLF clears the high current without overlapping, that requires extremely tight coordination margins. This is where manual calculations become prone to error.
Which brings us to the digital solution for coordination. The FastCT system. That's the fuse application coordination tool.
Yes, FastCT is the modern necessity for managing these critical systems. It offers a simple, real-time solution to optimize backup CLF selection. Engineers just input the specific transformer configuration rating, impedance, primary fusing, and the tool quickly calculates the required parameters.
And the practical output is something engineers rely on daily, time current curves, or TCCs.
PCCs are the graphical fingerprints of protective devices, and FCT generates these curves quickly and easily. By visualizing the TCCs of the expulsion fuse and the backup CLF, engineers can visually confirm that the protective margins between fuses ensure proper coordination.
In simple terms, they're guaranteeing that there is no gray zone where the fault current magnitude could cause both fuses to try to interrupt simultaneously, or worse, cause the wrong fuse to operate first and fail.
Precisely. This digital optimization is essential for reliability. It ensures that the CLF's high interrupting capability is applied precisely when the low current device is about to be overwhelmed, which minimizes catastrophic equipment failure and maximizes the lifespan of the transformer.
That really wraps up the critical coordination role. Now let's look closer at the two primary full-range fuse lines, the FX and the SX, and how their physical environment dictates their design.
Yeah, we're examining the same core technology, 50 Ka, hermetically sealed, damage sensor included,
Yeah.
but it's tailored for entirely different thermal and mechanical interfaces.
Okay, so starting with the TransGuard FX fuses, this is the general full-range workhorse. Where do we typically see the FX deployed?
The FX provides that essential dual overload and high fault protection in a single body. Its versatility is what makes it a workhorse. It could be clip-mounted in live front switchgear where it's exposed to air,
Okay.
housed in a dry well canister for transformer protection, or, as we discussed in the molded section, housed in the Elastomold Emelmian rubber-molded canister for submersible applications.
So it operates in air, sealed in a dry well, or sealed in rubber. A true generalist.
Correct. Its construction is incredibly robust, with that high-integrity hermetic sealing and machined brass end caps. However, we have to revisit the thermal derating, as the environment can change its performance requirements pretty significantly.
We discussed the standard air derating of 0.2% per degree C over 25 degrees C. But there's a very specific nuance for the FX when it's installed in a dry well canister submerged in oil. Why does this specific configuration require an additional derating A?
This is a critical point that is so often missed in design. When a dry well canister, which uses air or an inert gas as the insulating medium around the fuse, is fully submerged in hot insulating oil, the oil acts as a better insulator than air around the canister.
Meaning the oil traps the heat generated by the fuse inside the canister more effectively than air would.
That's it exactly. Oil immersion changes the thermal dynamics. It reduces the ability of the heat generated by the continuous current to dissipate away from the fuse body and into the surrounding oil. Therefore, the fuse requires an additional derating on top of the standard ambient temperature adjustment to prevent nuisance tripping.
And what are those specific additional derating percentages?
The maximum continuous current is reduced by an additional 2%. And this increases slightly to 3% for fuses that have a rated maximum voltage of 8.8 kV.
So engineers must not only use the temperature of the surrounding oil, but they must also factor in this 2% or 3% thermal penalty when they're calculating the maximum continuous current capacity for the FX fuse in this specific submerged dry well scenario.
It's absolutely crucial.
That tiny percentage is the difference between a reliable operation and a costly, frustrating nuisance outage. It just highlights how nuanced protection engineering really is.
It truly is. And one last thing on the FX. It does offer an optional blown fuse indicator. This is designed to operate without compromising the fuse's core arcing performance. However, there's a very clear instruction in the source material.
Which is?
This indicator feature is explicitly not suitable for drywall canister applications.
That makes practical sense. I mean, if the fuse is deep inside a canister that's submerged in oil, the indicator would be invisible anyway, and trying to incorporate a mechanism that's visible from the outside would just compromise the drywall seal?
Precisely. It's an operational specification that maintains integrity. So now we turn to the TransGuard SX fuses. These are the specialized components designed for a radically different thermal interface.
The SX is designated the wet well specialist. What does wet well mean, and why is that different from the FX in a dry well?
A wet well application means the fuse is designed specifically for installation in wet well fuse holders, where the fuse is submerged directly in the insulating oil.
So there's no intermediary air or gas-filled canister. The insulating oil itself is in direct contact with the fuse body.
Right. Usually inside pad-mounted switchgear or transformers.
That direct oil contact must impose a completely different set of thermal and mechanical demands, even though the high-integrity design is shear damage sensor, helium-tested seal, and so on.
It does. So the SX, the entire design is optimized for thermal dissipation through the oil, but it comes with limitations. Critically, we have to highlight the operational warning. SX fuses are not designed for any type of live switching operation.
Why is live switching strictly prohibited for the SX when we just saw the EFXE molded elbows that are designed specifically for hot stick switching?
Well, live switching involves intentionally drawing an arc in the presence of the insulating medium. Because the SX is designed to interrupt massive fault currents instantly under pressure, it's just not engineered to handle the repeated lower magnitude, sustained arcing that occurs when you're switching a load.
So attempting to switch live with an SX could result in uncontrolled arcing, oil splashing,
or damage to the wet well holder, compromising the entire enclosure. It's a major risk.
So they're purely fault interruption devices in a static, submerged environment, requiring the system to be de-energized before any operation.
That is the crucial distinction. And regarding its thermal capabilities, since it's operating fully submerged in oil, the SX's maximum continuous current is rated for oil immersion at 60 degrees C.
Okay, so 60 degrees C becomes the new baseline instead of 25 degrees C. If the oil temperature rises above 60 degrees C, does the same derating rule apply?
Yes, the consistency is maintained. If the oil temperature exceeds 60 degrees C, you derate by 0.2% per degree C over 60 degrees C.
And conversely,
Conversely, if you operate in a cooler climate where the oil rarely exceeds, say, 40 degrees C, you can actually re-rate the continuous current capacity up by 0.2% per degree C under 60 degrees C. The consistent application of these thermal coefficients ensures that protective margins are always respected, regardless of the operating environment.
this entire discussion has really underscored the difference between, passive fault protection and aggressive fault energy limitation, and the level of engineering required to achieve the latter.
That is the essential takeaway. Modern electrical distribution systems are increasingly prone to higher available fault currents, and they absolutely demand protective devices that don't just wait for a natural current zero crossing. They have to actively limit the destructive I²T energy by clearing faults in less than one-half cycle.
We saw how that speed is enabled by a really complex internal anatomy. That combination of low and high current elements and the rapid arc quenching provided by the highly compacted quartz sand. And the integrity of the components is non-negotiable, reinforced by features like the damage sensor and that highly sensitive helium mass spectrometer leak test to ensure reliability in submerged hostile environments.
And we saw how targeted application can completely revolutionize reliability metrics. Products like the Fused Load Break Elbows, the EFXE, directly contribute to better SAIFI scores by intelligently isolating faults to a single tap, preventing system-wide outages.
All while integrating high-speed fusing and hot stick operable switching into one fully sealed unit. It's an amazing piece of tech.
It is.
And the layered safety is so critical. The non-negotiable two-fuse protection scheme expulsion fuse plus backup CLF like the OS Shorty or EXT is just vital for high-value transformer assets. The CLF's job here is uniquely focused on limiting the energy to a value below the transformer tank's withstand capability, preventing that catastrophic rupture.
And we learned that coordination isn't just about timing, it's about communication. The brilliant engineering of the EXT to ensure coordination meant allowing that tiny bit of let-through energy to cause the series expulsion fuse to drop open, providing that essential visual fault indication to field crews.
Then we closed on the critical environmental specializations, the FX handling dry installations and drywall canisters requiring that unique additional depurating when it's submerged in oil due to trapped heat.
And the SX dedicated to direct wet well oil immersion, optimized for oil heat transfer but strictly prohibiting any live switching.
The entire operational ecosystem relies on selecting the right fuse, ensuring coordination, and strictly adhering to the thermal limits, all while maintaining that core capability to handle faults up to 50 kA or even 100 kA in specialized EXT applications. It brings us back to that massive performance gap that started our conversation. We saw the data confirming that traditional expulsion fuses, the ones still widely deployed, have maximum interrupting capabilities ranging only from 600A to 3500A.
While the modern current limiting fuses we discussed today are engineered to handle fault currents 15 to 30 times higher, up to 50,000 A or even 100,000 A.
Given that vast difference in fault management capability, here is the final provocative thought for you to consider. If a utility is operating a modern feeder with high available fault current, but it's still relying on those traditional low interrupting capacity systems for local protection, how often might those systems unknowingly be operating right on the brink of catastrophic tank failure during a high magnitude fault event, relying purely on a remote, distant, and comparatively slow upstream breaker to save the day, instead of the immediate, aggressive, and localized energy limitation offered by these high-tech CLFs?
The margin for catastrophic error in those legacy setups it's alarming. The full-scale adoption of high-interrupting CLFs isn't just an upgrade. It's a necessary philosophical shift from merely reacting to electrical faults to proactively containing the destructive energy they release. And that is the only way to ensure grid resilience and safety in the 21st century.
A crucial piece of knowledge to have in your operational arsenal. We appreciate you taking this deep dive with us today.